and all sorts of nasty stuff, really. That's what I do.
So thank you. So we slowly get to know all the people in the groups. Thank you, Adriano. So let me, how many are we now? 1, 2, 3, 4. 11. I think Rolando is still missing, right?
Yeah.
And
I think Katie is not here, no? Cozy Katie.
Yes, Cozy. Yes. If in Kigali, if you know about him or if you can contact him to make sure that he joins us. Let's wait 1 more minute.
Hello. Hi. So it's a bit lagging, I think.
Sorry?
It's lagging a bit, I think.
The internet is slow, or?
I'm not sure. It's intermittently lagging. Hopefully we can manage.
Anyway, now Tassien is the first, right?
Yeah, Tassien is the first, yeah.
Oh, I'm not the first. Yes. Yes. Okay. I'll relax a bit.
Yeah.
So I don't see neither Rolando nor Casey hearing, so I have a way to contact them. I will check my email just to make sure there is no problem. No, I have not received any email.
Me neither.
So I think we should start then.
Yeah.
So the first speaker today is Tassien, and he will talk about comparison of superfluidity in helium-4 and Bose-Einstein condensation. So I will now mute myself, and Tassien, you can share your screen and unmute yourself. Tassien, are you there?
Yeah. Can you see my screen?
No, not yet.
Let's wait 1 more minute. I started screen sharing, so we have a writing. Maybe it's a bit slow, so let's wait. Here it's still black. I see it's still black. Oh, oops. Can you stop sharing and restarting the sharing, maybe? Oh, in the meantime, Rolando has appeared, so good morning. Okay, now.
Yeah.
Okay, thank you. So you can start.
Hello. Hello, everyone. Hello.
Yes. Yes, Tasin, we can hear you.
Here, you can start, yes.
My name is Tasie Hamaholo. About my academic background, I did my Bachelor of Physics. Sorry? I did my Bachelor at the University of Rwanda, College of Science and Technology. Can you hear me?
Yes, very
Sure.
well. Please go on, yes.
Yeah. I did my BSc at University of Rwanda, College of Science and Technology, Kigali, Nyarugenge campus. Currently, I'm doing my master at University of Rwanda, East African Institute of Fundamental Research. About my presentation today, the title is Superfluidity in Helium-4 and Bose-Einstein Condensation. Yeah, this is my university. Superfluidity and Bose-Einstein condensation are among the most fascinating phenomena in nature. They have surprising strange properties that are direct consequences of quantum mechanics. In my talk, I start with a brief story of discovery of superfluid helium-4. Secondly, I discuss non-interacting bosons. Third, we discuss boson-Einstein condensation. Then, we do comparison between the two phenomena. We start by brief history of discovery of helium-4 superfluid. In 1908, Herc Kemmerling owns liquefied helium. He found that helium liquid is distinctive from other normal liquids because it undergoes phase transition at around temperature 2.17 Kelvin. He called these two phases, you can see, one is helium, he called them helium-2, the other one helium-1. You see this phase diagram, it does not have a triple point. So this is his finding. However, his interesting results, no one who cared about it until in 1938, when Paito Kaptisa discovered that this helium-2 is a superfluid. This has already proven independently by Allen and Donald Misner. That was the history. Now we go to discussion of non-interacting bosons or boson gas. Any system particles, any boson particles, they should obey Bose-Einstein distribution. This is Bose-Einstein distribution, this occupation number. You can see this expression, this is it, a function of chemical potential, as it is called the fugacity. For a free boson, the energy is given by this. If you want to find the total number of particles in a system, we should sum up all possible k states. Whenever we want to do this sum, in the limit, in the thermodynamic limit V tend to infinity, this sum, we expect it to be changed into integral. When we are doing that integral, we encounter this function. We find that the total number of particles are related with this function G3/2, which is called the Einstein function. So we cannot deal with this without seeing how this function changes with chemical potential, if Z or chemical potential. You see this?
Just a minute,
function?
Tachin. So is there any typo in the equation? So you have written Z to the
Typo?
power beta E in equation 1 upon Z inverse, where you define Z
Yeah.
equals to e to the power beta mu.
Question 1.
Yeah, equation 1. And then you wrote
Sorry.
that Z to the power beta E. Shouldn't be e to the power beta E?
I see a question 1.
Okay, can you?
Sorry?
Hello?
Hello?
Can you hear my voice? You, am I
Yeah,
audible?
I'm hearing you, sir.
Yeah, yeah. I am ma'am. Okay, I'm Sukanya. Okay. Anyway, so what I wanted to say that in equation
Ma'am.
1, I just have one doubt that you have written. So actually the Bose-Einstein distribution, it should be 1 upon e to the power e minus mu divided by kbt minus 1. But it's okay, I understand there are different ways to write it, like beta is equals to 1 by kbt, which you should have written somewhere. No, my doubt is it z z to the power beta ek? I don't understand this term. Shouldn't be e to the power beta e?
Yeah, this is the power beta times the energy, this expression here.
Okay.
This is the power minus 1. This one is another independent term, is not an exponent. Is it okay?
No, the comment was the second Z should be an exponential.
Yes.
Oh, this.
No, the second Z in the first equation.
This one here.
Yes,
Oh,
the Z is an exponential.
this.
Yeah.
Oh,
Yes,
yeah.
that was a
It's
typo.
exponential.
Okay.
Thank you. Type.
Yeah, this I just, this is the typo. Okay. Yeah, carry on, please. Yeah.
Okay, I can go on. This function, Einstein function, is changing like this. You see, it has infinite derivative at z equal 1. So from here we can see how n is related to chemical potential. Chemical potential at high temperature, we can this equation 4. You can this equation 4. We can expand it, and we get this equation 6, relating chemical potential and temperature. This is how chemical potential is changing with temperature, but we see that if we cool down and we reach this TC, critical temperature, the Z will increase and reach 1. In this case, when Z is equal to 1, the chemical potential will become 0. Okay, as soon as chemical potential becomes 0, we will see that as soon as chemical potential becomes 0, number of particles in a ground state will reduce to this. So they will know, it means that Einstein realized that there is at k equal to 0, the number of particles in the ground state will be infinite. So we get this opportunity to collect this, and we write the total number of particles as a sum of the particles in a ground state plus the other here the other particles. Here k should be different from 0. This question 10 is equivalent with this. You can see this figure shows this peak shows the change in density when we are cooling a gas. When we are cooling a gas, the density change like this. You see this first figure here is when you have temperature of gas is greater than a critical temperature. Here is when the temperature of gas is around the critical temperature, and this case is when we are below the critical temperature. So this experiment shows what happens when we are cooling a gas below the critical temperature. Yeah, this critical temperature is the temperature at which we have that chemical potential equal to 0. So now we can talk about superfluidity. Talking about superfluidity, we should first understand why superfluidity in helium-4 is a quantum effect. Okay, here we consider two noble gas atoms, helium and neon. To see classical quantum effect, we can base on the interatomic spacing, typical interatomic spacing, and the Broglie wavelength. With the mass of helium and at small temperature, we can see that helium has 0.4 nanometer. The Broglie wavelength with the separation, it is close. But for the case of neon, we see that interatomic spacing is much greater than the wavelength. In this case, we can see that the quantum effect in helium are much significant than in neon. So we can, that's why we should treat helium quantum mechanically. Yeah, this graph shows the Lennard-Jones interatomic potential in a gas. It is one of the potential that is reasonable to represent noble gases around equilibrium point. You see that this neon has the big binding energy, while helium has small binding energy. Together with its lighter mass, so it will exhibit quantum effect more than neon. So, we go on. Here we discuss the properties and some applications of superfluid in helium-4. Helium-4 appears to have a zero viscosity. It can flow with zero change in pressure. It appears to rise side of its container. It has zero entropy and extremely high thermal conductivity. This is high fountain effect is thermal coupling effect in a fluid. I will discuss this. About applications, here I can mention like it can be used as a quantum solvent. This is because of these properties. We can mention some application depending on the properties of material. This is a medical purpose earthquake prediction. You can use to calculate exact gravitation effects of our planet. Here, because it is highly thermoconductive, you can use as a field magnet. Okay, here I discuss one of the properties. Amazing property called the fountain effect is the result of thermal coupling effect. For example, if this is the area with the box of our fluid. If you can place a good absorber of heat in this place, when we heat that material either by any radiation, so we will see a rise in this fluid or more. This experimental facts. So now I can go to similarities between Bose-Einstein condensation and superfluidity. Oh, we can helium-3, which is a boson, does not become a superfluid around 2 Kelvin. Yeah, this is because is a fermion when helium-4 is a boson. So we are talking about boson with Bose-Einstein condensation. The second similarity I can say here, if we use the result we got on Bose-Einstein condensation, we can estimate roughly the critical temperature of superfluidity in helium-4. Here, you see this is a typical interatomic distance, so the atomic density can be roughly approximated like this. This formula is what we got on Bose-Einstein condensation above. So this value, encountering that we didn't consider interaction between particles, is roughly somehow matching the critical temperature of superfluidity. Now we go to the differences. Yeah, the differences between these two phenomena about these heat specific heat capacities. We can see that at low temperature, if we see this is the heat capacity of Bose-Einstein condensation. This is for helium-4 superfluid. You see that at low temperature, here the specific heat goes as temperature power 3/2, while here we have to go as temperature power 3. Even around here we see have a sharp, when here we have a normal change of CV. Now we go to, okay, thank you. That's the end of my presentation.
So thank you. So now,
Any question?
yes, now it's time for questions. So is there any question? Ivan, I see your microphone is open. Do you want to ask a question? Okay, that's the best way to get it switched off.
Questions from students? Anyone? Okay. So I would like to know what is the order of phase transition for He4 from normal fluid to superfluid?
Sorry, you would like to know?
What is the order of phase transition for helium-4 from normal fluid to superfluid? Because there is transition, right? At the critical temperature below a certain temperature, which you showed as 3 Kelvin, it becomes superfluid, He4. So what is the order of this phase transition?
Thank you. The order of this phase transition is the order 1 because we have a discontinuity in this specific heat here.
Okay. And there are also other isotopes of helium, right? So like He3. So do you know what is the critical temperature at which
Sorry?
there are also other isotopes of helium?
Yeah, there is helium-3 isotope.
Exactly. So do you know
Yeah.
the transition temperature for helium-3 from normal fluid to superfluid?
It is around 2 millikelvin.
Right. So it is quite low, right?
It is,
Very low than He4. So do you know the reason
yeah,
why
it is.
it shows superfluidity at extremely low temperature than He4?
Honestly, I don't, but I didn't concentrate on
Because
fermions.
what is the difference between, if we can think that what is the difference between He3 and He4 could be the answer, because so how they do differ, He4 and
Okay,
He3?
because for H4 it's a boson, so in ground state we can the ground state we can static as much as depending on the volume of the container.
Yes, it is because the
Yeah, we can
difference in the
condense
neutron
particles.
number and difference in the
For
spin. Yeah.
H3, yeah.
So can you show your figure 5?
5.
Figure 5, when you show the density.
5.
Yes.
Okay.
I still don't see it. Are you showing figure 5 now?
Here.
The one where you see the peak growing below.
Figure 5.
Okay. Figure 5, yes.
Yeah, this is the figure 5.
I see the fountain effect now. I don't know if I have a delay or. I wanted you to show the one where you show the density growing below TC.
Of when we
Yeah, this
Yeah.
one. Yeah, exactly. Changing density.
when we are cooling a
You show the
gas.
density, but in which space?
Yeah, is this,
What is on the X and Y axis here?
oh, this picture shows the change in temperature. Of course, it is a picture I picked from internet, but what I wanted to show is how density is changing as we are cooling a gas.
Yeah, but what density? I mean, what is in the X and Y?
There are two.
Are we okay?
Okay, the X is you can say.
Is this in real space or in momentum space?
Okay, this is the momentum.
Yeah, that was my question. Okay, thank
It
you.
is the momentum.
Okay, this is a momentum space. So you see that the density. I mean, the density
Yeah,
going up
momentum.
in the zero momentum. Okay, yes, that was my question. So you said that the Broglie length of helium is 0.5 nanometers. Right? I think a few slides after this. But at what temperature is that calculated?
Sorry, I can't hear you.
Well, a few slides after these, you show the Broglie temperature, lengths of helium and neon. No, you make a comparison between the two. Can you show that slide? Did you hear me?
Yes.
Okay. So can you show the slides when you talk about the de Broglie length? Yeah, exactly.
Sorry.
So these values are calculated at what temperature?
Oh, I can't hear.
Uh,
Sorry, sir.
no, the slides was the correct one. Don't change it. I'm talking about the slides where the de Broglie length is shown.
Previous slide, please. Yeah, just go back.
Tassien, can you hear us? I fear we have a
Yeah, I think.
problem. Let's try to type.
Hello?
Yeah, this slide. Yes, perfect. Yeah.
Okay.
Hello?
Yes. Now we can hear you. No, the
Not
slide
really.
about the de Broglie length.
Hello?
Yeah, can you hear us? No, probably not.
Okay. I can't hear you.
Yeah, please look at the chat.
You want me to do what?
Can you show the
Please.
slides where you calculate exactly slide 9 where you calculate the de Broglie length?
Okay. Okay, here. You want to okay. You want me to show you how I calculated this?
No, well, it's written there. No, you show the equation of the de Broglie length. I see the fountain effect now. So yeah, these de Broglie.
Yeah, for example, the way I calculated the blow wavelength of helium.
Well,
I just inserted the mass of helium.
yeah, okay, that's clear.
Yeah.
You have a formula there, but what temperature did you use?
What? What?
Temperature.
Hello?
Yes.
Okay, the temperature.
Yes.
The temperature here, it is the temperature I used here is this around 4 Kelvin degree.
Ah, okay. The one at the relevant.
The melting temperature of helium here.
Okay. So how much would it be at 400 Kelvin? So if the temperature becomes 100 times larger, what would be the Broglie length?
If the temperature becomes 100 times.
100 times larger. So
the Broglie wavelength. The lambda will be divided by, it will be, if we multiply temperature by 100, lambda will be 10 less times.
Yeah, okay, yes, 1/10. Okay, yeah. Okay. So
hello?
Yeah, I heard your answer. I'm satisfied. So what do you mean by medical applications and earthquake prediction? I didn't quite understand how this could be used for those applications. Can you tell us one sentence more?
These applications are related to these properties. In medical purposes, for example, we can, for sure, I didn't know how the working mechanics may be behind these all applications, but if I can say medical purposes of application of this superfluid, it is effect due to this property of for example, of high thermal conductivity. Or we can high thermal property.
So how could you use it for medical purposes? Can you give us in 2 sentences an idea of what the idea behind is? How would you use a material, something with high thermal conductivity for medical purposes?
In medical purposes.
Yeah, how? I mean, for which properties it is useful for medical purposes? That is not quite clear to us.
Hello?
Yes.
Yeah.
Did you hear our questions? We have no idea what you mean by.
Yeah, I heard your question.
Okay.
Okay, I have heard the question. Because I didn't look at it very well, I was still thinking how I can answer it.
Okay, I mean, just say don't know, because I don't think we can find out now
Yeah.
a way to use it if you don't know. So let's move on. So you say helium-3 and helium-4. What does this 3 and 4 refer to?
Yeah.
Yeah, tell the difference between He4 and He3. What are they actually? What is the similarity and what is the difference between He4 and He3?
Did you hear our question?
Yeah, I don't know.
Okay.
They are the isotopes. So you know what is isotope, right? They are the isotopes of helium. So they have same proton numbers, but they differ by the number of neutrons.
So how many protons does helium have? Okay, so helium is, did you hear our question first? Or?
Helium-3 and helium-4.
Yes, so tell us a bit more.
Sorry, helium-3 and helium-4.
Yes, yes. So how many protons do they have? How many neutrons? And what is
What are they? I don't know why I can't hear.
How
So-
many protons they do have? Helium-4 and helium-3.
The similarities and differences.
Yes,
Oh,
yes.
okay, H3 and H4.
Yes.
Yeah, they are isotope, but helium-4 has 2 protons and 2 neutrons, while helium-3 has only 2 proton and 1 neutron.
Okay. Okay.
Okay. Okay. Good. Yeah, that's what.
But they all have the 2 electrons.
Okay. So are there other questions? Anyone?
There is a quick remark that I would like to make, and it concerns the transition between helium-1 and helium-2. I thought a question was asked before. The transition is of second order. It's not first.
Yeah, I also thought so because it's continuous. Yeah.
Yeah.
It's not a divergence there. It's a discontinuity in the derivative of the.
Yeah, but
In
it
the
makes,
second derivative. Yeah.
which is a specific heat, which makes sense because it's the second derivative of the free energy and stuff like that. So it's the second order one. I also think somebody asked why you see Bose-Einstein condensation or superfluidity of helium-3 at much lower temperatures.
Yeah.
That was a question too, right? What I know is that helium-3 being a fermion does not have the same characteristics in the ground state as helium-4. So if you want to see superfluidity, which is a pretty much bosonic feature, you need to create pairs of atoms of helium-3. These pairs are bosonic, they undergo superfluidity, but they happen at a much lower temperature. That's why.
Yeah.
Thank you. Thank you very much. So other questions, comments? So.
Okay, I have a question.
Yes.
Okay, I listened to your presentation, and I still have no clue on what is really Bose-Einstein condensation and superfluid. Will you give just a quick definition on what these are? Are they concepts or method that you use to determine the properties of some system, for example?
Is that a question goes to me?
Yes,
Coming
yes,
to me?
yes.
Okay. Okay. The Bose-Einstein condensation is a phenomena that happen at low temperature, at very low temperature gas, when the chemical potential drop to zero, all particles, most part of particles occupy the ground state. Yeah, all particles occupy ground state of momentum equals zero, so they condense together. So the density, it changed, become large.
Density of
Is it okay?
no, the density of what?
Yes, of a system of particles. For example, you have a box.
Yeah.
You trap the gas in a box. You start cooling it. So so the density of gas become huge because almost of them tend to occupy the ground state.
Okay. And how about the superfluidity?
Okay, about the superfluidity, it's also a quantum effect that the even it about normally we know the normal fluid, or as we cool them, they become solid. But the superfluidity phenomena occurring in helium-4, even it is around zero temperature, it is still liquid. Helium is still liquid.
Okay. So oh, can I speak?
Oh, sorry.
Yes.
Okay. I say, what information can we extract from the graph of the CV? You have calculated CV, I think, at the last slide.
This.
No, the last one.
Are you saying this similarity?
No. The CV,
This.
yes. Yes. So what is the difference between these? What information can we extract from the fact that we have calculated the CV?
Sorry?
Yeah, I mean, you have calculated CV for in the case of Bose-Einstein condensation and superfluidity. So what the information that I can extract from this? You have the value of CV for Bose-Einstein. You have the value in the case of superfluidity. So what information that gives us, physically speaking?
Can you repeat your question?
I say, what is the difference between the two graphs that you are presenting here?
I can't get you, please.
Can you hear me? Are you here? Hello?
Maybe you can write, Julia.
No.
Okay, that's okay.
Yeah, I don't know I don't know whether it's my internet problem or yours. I don't know what's happening. There is a jump in your speaking. It's not discontinuous voice. You are asking me to. I can't get you. I don't know. Maybe I don't know
Hello,
why.
Tassien. Tassien?
Yeah.
Okay. Can you hear me clearly?
Yeah, I'm hearing you. Okay. If you
Okay.
have heard her question, please tell me.
Yes, that's what I want to repeat now. You have two graphs on page 13. Page 13, you have two graphs there, two plots.
Two plots, yeah.
Yes. What is the difference between the two? What information can you extract from the first?
Okay.
And what information can you extract from the second?
Okay. Okay. Then I have heard. I can answer her if she's hearing me.
Okay.
Okay.
Yeah, I'm
You see?
hearing you.
Okay. The first graph, you see. Here I'm mentioning the differences between the two heat capacities. As you see, the first heat capacities, there is the I didn't put it there how this function goes, but here this goes as T power 3/2 at low temperature. Yeah, while here it goes like T cubed. What I can conclude from here is just that these heat capacities are different. This has high thermal conductivity than this. Okay, when below Tc, the thermal capacity increase with temperature. And it is extremely high at critical point. I don't know what information else I can get from this. I think if it's not the answer you are expecting, someone can help me. Hello?
Well, I don't have more to say. I don't know if Adriano wants to say something.
No, I don't have any questions. We can go forward.
Okay, so if not, then
actually I have a question.
Yeah, please, yes.
Yes. You say that in both Einstein condensation, this in this and we have the chemical potential equal to 0, and all the particle is in the ground state. So can you connect the physical meaning between when we have the chemical potential equal to 0 and we have the ground state?
Is okay. The chemical potential equal to 0 means that you can. Okay, there is no cost to put all particles together. There is no cost to put all particles in the ground state. That's the physical meaning of chemical potential being 0. So because normally, in order to condense particles together, to give 0 momentum to particles, it requires you a cost. When the chemical potential is 0, it means that there is no cost.
I see.
Yeah, I think the impressive thing is that you have a macroscopic number of particles all in the very same quantum state. So that's the impressive thing. So I think if there are no other pressing questions, we should comment on the talk and move on. Kanya, do you want to comment?
Yeah, I would say that in the beginning, when you have described the equations, so instead of writing only equation numbers, you should write the symbols also, what specifies what, and also a short note beside each equation, just which equation signifies what. That then it would be easier to follow. Like also as example, you write KB. There is no information what is KB, the Boltzmann constant and all. I mean, you also haven't specified which symbol is for what, where you have written equations.
Yes, then
which question, please?
In the equations.
Like you have a slide, no? So go to the slide where you have written, I think, 3-4 equations, like B distribution, Bose-Einstein distribution and all. Yeah, for example, this slide also. So it would have been better if you have written,
Please.
yeah, I wanted to say about this slide. So in the beginning, just try to at least say which symbol signifies what, or just write in a smaller font in your slide, what is what, like what is beta is equals to 1 by kbt, and what is kb, all these things. So
Yeah,
it
yeah.
would be easier for the audience to
I noticed
understand.
them.
Yes.
Yes. So other things you probably
Thank you.
noticed from the question is you could have defined what these things are at the beginning, no? So what is a superfluid? What is, then you can say it's a quantum effect, okay, but first define them. I think in front of this audience it makes sense. Then the other thing is, don't put things if you don't know what it means. I mean, the medical purposes, the electrical prediction, nobody would have asked you that if you hadn't put that. So if you don't know, just don't put it, you know. So and I think in many figures like this one, there is no reference. Did you do this figure yourself, or did you take it from somewhere? So put the reference below, so the precise website where you took it, even if it's just some website on the internet, that's fine. But, yes, and I mean, interesting fact and interesting things. So yeah, that's all from me. If there are no other comments, let's move to the second talk. Thank you, Sasien. So let's
Thank you.
from here.
Thank you.
Thank you. Let's move to the second talk by Joshua. We'll talk about a pedestrian's guide to entanglement detection theory. So, Joshua.
Wait. Can everyone see this slide?
Yes.
Yes. Yes.
Okay. I'll do this again.
What am I going to do?
Okay. Okay. So, should I begin?
Yes. Please, Tassien, mute yourself.
Okay. Okay. Sorry. Okay. So, good
Can I
afternoon.
do it?
Yes. Yes. What is it? Sorry. Sorry.
Tassien, could you please mute yourself?
Okay. So, good afternoon, everyone. I'll be presenting something about the entanglement detection theory. So, it's pedestrian guide. I wouldn't want to go on to the math too much. I just want you to appreciate what's with entanglement and how does scientists do entanglement detection theory. Now, we often joke that
Sorry? Hello?
yes. Can
Sorry, I cannot see your slides. It's black, just black.
really? Okay, let me
Is it just me?
I don't know.
I see it, but still, just try to share again.
Okay. Where is it? This one. Okay, is it okay?
Okay, nice now. Thank you.
Okay. So yeah, we often joke about making some presentation or um, paper about entanglement. We should. It's always a compulsory to add the paper by Einstein, Podolsky, and Rosen in 1935. It's about the discovery of entanglement. Entanglement is quite different since it was first found theoretically, unlike other quantum phenomena, which, for example, um, the violation of the ultraviolet catastrophe and so on. Entanglement was found in paper. And even then, the experimental verification of entanglement it took about 50 years or so to be conclusively verified. At the time when Einstein, Podolsky, and Rosen made this paper, it wasn't even called entanglement. The name entanglement was was coined by Schrödinger in the same year, 1935. And even then, it's not even the entanglement that the usual popular media often portray. And Schrödinger pointed out that it must be an entanglement of predictions. No, we'll talk about it later. Entanglement is quite famous, with Einstein calling it a spooky action at a distance, and it's quite related to Schrodinger's entanglement of predictions. Uh, okay, so we now begin with some key assumptions for our talk. So the first one is superposition principle. Now we note that the superposition principle arises since the Schrodinger equation is a linear differential equation, and so we can have a linear combination of solutions and a superposition in it, and it's still a solution to the Schrodinger equation. Now our next assumption is that a quantum wave function, or in any language, is a quantum ket vector or a density operator. It must describe fully the entire state of a composite quantum system. So all the knowledge that we need to fully describe a quantum system is encoded in the wave function, ket vector, or the density operator. Finally, is that any state evolution on one subsystem, assuming that the composite system has, say, two subsystems. So any evolution any evolution on one subsystem should not affect the state of the other. Now, this is one can show it that such evolution is unitary, and it only works for unitary evolutions. And this also assumes that whatever we do on one subsystem doesn't affect another. It means that they are spatially separated, and that anything that we do on one is local on it, and whatever we do on another subsystem is local to it as well. Now, for our case, we won't use the example made by Einstein in 1935. We would use a Gedanken experiment by Bohm and Aronov in 1957. So this is a Gedanken experiment consisting of two spins. Now suppose we have 3 participants for this experiment. So we have Alice, Bob, and Charlie. Now for our first case, we consider Charlie, in which he prepares 2 non-interacting particles. So it could be whatever. And they are non-interacting. So the state of one particle is independent of the other. And suppose that one particle has a spin. So it could be either up or down. Of course, it's by the superposition principle. And suppose that it happens either 50% 50% spin up or 50% spin down. So Charlie sends one to Alice, and then Charlie sends another to Bob. Now we would disregard Charlie now and just focus on Alice and Bob. Now Alice makes a measurement on the spin, measures it on the z direction. It means that we have this polyvector, poly matrix, which is defined to this one. And Bob also independently measures his spin, again using the same poly matrix, this one. And then they tabulate the results. So we do this, they do the experiment plenty of times until, say, n large, whatever. And so they find 3 things. First is that Alice finds that the results do not correlate, in a sense that everything is random. So what Alice gets in her measurement is that the average of her measurements is 0. Similarly, for Bob, he also sees no correlation in the measurements that he's done. And so it's completely random. And so it could be either positive or negative, +1 or -1. And so the average is also 0. The next thing that they do is compare their results. So they meet at some point and then compare their results. And notice that they also notice that there is no correlation between joint measurements. So for example, if Alice gets a positive one and Bob gets negative, and for the next one it's negative and positive, and it's completely random. So overall, the joint measurement, the average of the joint measurements is equal to 0. Now, it's uncommon in that time what we mean by two non-interacting particles, but for us, we have the advantage of knowing the math. So Charlie prepares the state in this form. So we can see that the first particle is defined as a superposition of plus and minus, of spin up and spin down. And also we can see here that we have a superposition of the state of the second particle, which is again, either it's a spin up or a spin down. And now we now consider a case in which we have two interacting particles. So Charlie now prepares particles in such a way that if one is spin up, the other must be spin down. And if he prepares the other to be spin down, we expect that the other one is spin up. And then what he does, and he again distributes this particle to Alice and then distribute this to Bob. And then we do again the same measurement scheme. So Alice measures it in Z, and again Bob measures it in Z, and then we do it plenty of times. And then what's interesting is that we still retain the same result. So Alice still finds a completely random results. So again, the average is 0. Now Bob also finds it the same and finds that the average is also 0. But what is interesting here is that if they compare their measurements, yes, sorry. Right, okay, sorry. So I'll continue. So if they compare their measurements, so they find that the average of the joint measurement is -1. So we have an anti-correlation, and it always happens, whatever the trial. No, so whatever experiment with n trials we do, we have this anti-correlation. Now this is interesting. If we express this state produced by Charlie in our language today, we find that we have this so-called singlet state. So using this notation, we can find that it's indeed entangled. One cannot factor this. Okay. Now, this is nothing strange. One can use, say, Charlie can just use, say, one coin instead of just particles with spin. Say Charlie gives Alice some coin, and Charlie gives Bob a coin as well. So these two coins could either be, say, +1 and the other one is -1. And if Alice looks at the coin and knows it's +1, then she immediately knows that Bob's must be -1. And you can repeat it the same. Can repeat the same trial over and over. And it's the same case of entanglement. Now, what is the difference between that case and this case? The difference is mostly on the concept of measurement in quantum mechanics. So measurement plays a key role in quantum entanglement. So if we again consider two non-interacting particles from earlier, for this case, we don't measure, Alice and Bob doesn't need to measure on the Z direction. They can measure on X, Y, and Z. So it could be anything. And if you calculate the joint measurements, the average of the joint measurements is still 0. And that's to no surprise. But if we consider the interacting particle case, we find that, say if Alice measures in the Z direction and Bob's measure in the X direction, we find, and we do it plenty of times, they will find that the joint measurement is 0, which is quite weird. If Alice measures in Z and Bob measures in Z, then we have an anti-correlation. So it's interesting since we find that it's somehow the choice of Alice's measurement uh, affects that of Bob's, in the sense that if we compared the measurements, could be either an anti-correlation or just something random. So there is a question now, since we have this sort of weirdness. So the question now is: are we missing something in our description of our experiment? So perhaps Charlie has prepared the two spins in such a way that we have this sort of statistical correlation in measurements. So without Alice's and Bob's knowing. So the result, if we have Alice's measuring in X and Bob's measuring in Y, so probably Charlie has predetermined it, and that whatever Alice's and Bob do, they will have the same correlation. Now, Einstein proposed in some of his correspondences, but not really in publication, a sort of a local hidden variable in which it might completely describe what's missing from what we've discussed earlier. So probably Charlie might have introduced some hidden parameter that is not known to Alice and Bob, such that the supposed statistical correlations that arise, the anti-correlation, the random thing, can naturally occur. So to give a demonstration, suppose that we have these two non-interacting particles again. Charlie, supposing that he added some hidden parameter to those two particles. So Charlie sends one to Alice and Charlie sends another particle to Bob. And then they do the measurements again. And notice again that everything else is, again, what we note earlier, the averages of their measurements and the joint measurement is just 0. Now, what hidden parameter can we attribute to this? No, lambda could be anything, but what we know from the start is that the particle, each of the particle is randomly, can be randomly made, since it's just a superposition of a plus and minus. So that we can assign. So one thing that's crucial about it is that prior to measurement of Alice and Bob, the states have been separately predetermined. It's been predetermined by some hidden parameter. That's the crucial thing here. Now, if we compare it to the entangled case, it might be different. In the 1964, Bell actually introduced a mathematical construct for the local hidden variable model, and also introduced a so-called Bell inequality, which to demonstrate what does the system need to satisfy in order to satisfy the local hidden variable model that we've discussed. So the Bell inequality we defined here is actually a modern description. So we have this inequality here where A1, B1, A2, and B2 are the measurement directions chosen by Alice and Bob. So this works not just if Alice choose X, Y, and Z. It can work even if we choose an arbitrary direction of measurement. So Alice can even choose a 45 degrees with respect to Bob's, and it will still work. Now, what is interesting is that if we consider two interacting particles, whatever, as long as they're interacting, It may the conditions of the measurement may violate the Bell inequality. So in fact, so in this case, if we have interacting particles, then there might be a scenario in which we violate the Bell inequality, and therefore we cannot attribute a hidden parameter model to it. So in that essence, we consider the system to be we consider the two particles to be entangled. Now, if we attempt to make do with the local hidden variable model and assume it's true all the time, then we must have a mechanism in which the measurement done on analysis should instantaneously affect the measurement done on Bob's, and that's a bit weird in a sense. So it's somehow violating concept of locality since one influences the other. Yes. So this took about 20 years for it to be experimentally verified. But in fact, one crucial thing here is that you won't find this violation if you choose just X, Y, and Z directions. The maximal violation of the Bell inequality is if you have a 45-degree a 45-degree setting between the two detectors. So the first conclusive verification was done by Aspect et al. In the 1982, and it didn't use spin entangled particles. They used what they call as polarization entangled photons. So it works still the same, essentially. So could be that the polarization here is vertical and the other polarization is horizontal. And then we do the measurement again, as with the Gedanken experiment from earlier. And we find this, and they found that this plot here of the correlation, the blue one, and comparing it to the local hidden variable version, which is this straight line. So notice that this correlation here accurately predicts, is accurately predicted by quantum mechanics. And these special points here are the corresponding to the maximal violations of the Bell inequality. At this point here, which is a 90-degree, which is if Alice say measures in the Z and Bob measures in the X, at those points you won't find any violation of the Bell inequalities. Now, there are also experiments, it's still ongoing, so verifications of Bell inequalities are still being made. For example, by Hansen et al. It was done in 2015, and it uses spin entangled states, but I don't want to go into detail. And then we also have, for example, Roch et al. And it was done in 2018 by exploiting a Bell test using high redshift quasar. So I don't really know exactly. But why do we do this experimental verifications still now? But it's because there are also loopholes in those experiments. So for example, one loophole that we need to overcome is we need to ensure that Alice's and Bob's experiments do not communicate with each other, essentially. It means that if Bob learns that Alice had done a measurement, there mustn't be a time for Bob to adjust his settings so that he complies with the local hidden variable model. So the next thing is they must also ensure that whatever Alice does on her subsystem, it mustn't be correlated with Bob's. So that concept is related to free will of the observers. one interesting application of the Bell inequality is a quantum key distribution. So it's a highly secure um, transfer of, it's a highly secure protocol in which, for example, if suppose that Alice and Bob has an agreed upon series of measurements. So for example, if Alice's measures in Z, then Bob's measure in Z. For the next, Alice measures in X, and Bob measures in X, and so on. And since we know that the result on one end is completely random, there is no way of knowing whatever the result is. So it could be plus, minus, plus, minus, plus, minus, it, and so on. So there is no way of anyone outside Alice and Bob that can determine the results. Now suppose that there is some eavesdropper, say Eve, who does a measurement on Bob's side before Bob does an experiment. So in essence, Eve Eve sort of determines the state of the particle on Bob's end before Bob does, and so the state on Bob's end is already predetermined. And so what it means is if this is predetermined, the state here is also can be determined by implying this, and so we don't have a violation of the Bell inequality. Now we know that if there is no eavesdropper, there is a violation of Bell inequality, since initially the two particles before Alice's and Bob's measurements are entangled. Now we know that since Eve knows the state, there mustn't be a Bell violation, a Bell inequality violation, and this can be detected by Alice and Bob by comparing their joint measurement, by comparing their results. So that's interesting, and that is highly secure. So yes. Now, so it took about some 20 years from Bell for entanglement to be formalized in sort of a mathematical way. So what it means to be entangled is to not be a separable state. So for example, if we have a composite system of Alice and Bob, then we say that they have a separable state if the state of the entire system can be expressed as this. Now notice that there is a consistency with Bell's idea of Bell and Einstein's idea of separable predeterminism. Sorry, since we know that Alice has a state of PA, rho A, and Bob has a state of rho B. So this itself is a product state. So we can completely separate the two states of Alice and Bob. So if we cannot express the state of the system as in this form, then the state is necessarily entangled. So there must be some correlation between the two systems of some sort. Using this formalism, Werner found that if we have this, if we consider this state which are unitarily invariant, so if we place a state here and then do this transformation, it ends up with the same rho. Now he found that these states do not violate the Bell inequalities, which is interesting since we have an entangled state that can admit a hidden variable model. So it hints that the Bell inequalities might not be a fundamental way of differentiating states which can be described by a separately predeterministic model, and those that have entanglement, which we cannot describe in a separable way. And so it leads to the development of entanglement detection theory. So entanglement detection theory is often described as in two ways. So the first one is we define a sufficient condition for separability, and then we take its contrapositive and we have a necessary condition for entanglement. So in relation to the earlier discussion, so the Bell inequalities showed says that if your system has can admit the hidden variable model, in this case, if the state can be separable, then they must satisfy this Bell inequalities. Otherwise, if there is a violation of the Bell inequality, then we have a condition for entanglement. So one way to visualize this is that suppose we have some separability criterion that's the term for a mechanism of which we can use to know if the state is entangled or not. So suppose that we have a separability criterion and that we have a sufficient condition for separability, which is so in this region inside this red closed surfaces, all the separable states, but there are also states in which that do not violate the condition, the sufficient condition, but are entangled. So these are the entangled states in which the separability criterion do not detect as entangled. So basically means that the criterion is silent to them and they don't know, and the criterion doesn't know what to do with them. However, outside this boundary, it is necessary that these are all entangled using the separability criterion. And this means that if you have some separability criterion, then it's not guaranteed that all of the states, all the entangled states can be detected by it. So there are some, but not all. However, there are some nice exceptions. So the first one are the collection of positive but not completely positive maps. So it is a sufficient and necessary condition for separability, but it is an exhaustive method since you need all of the maps to satisfy these two conditions. So raw is separable if and only if these are satisfied. Of course, since it's exhaustive, it's not really practical. So we don't normally use them, and we only use we only use some positive or not completely positive maps. But we also have the same problem from earlier in which not all of these maps can detect the entanglement of all the states. Now, one special case of these maps is the positive partial transposition criterion, in which the only necessary map that we need to consider for a qubit, a 2x2, or qubit, which is 2x3, the only map that we need to consider is the transposition map. And so if we find that these two are satisfied, so these two are called partial transposition maps, and then we know that rho is separable. So it's quite nice since you only need to use one map. Now the problem with this is that it cannot be extended to arbitrary dimensions. For example, if we go to higher dimensions, the PPT criterion, the positive partial transposition criterion, is just a necessary condition. So what it means is that for separability, you need this. Yes, you need this to show that this is separable, but it cannot sufficiently make it cannot sufficiently show that rho is in fact separable. Now, in fact, if we go to a Qtrit system, the PPT criterion cannot be generalized there. So it's impossible to do it in 3x3 systems. Now, what is also interesting with these maps is that they cannot be represented as a physical process, since they are not completely positive, which means that they do not represent any physical process and that they cannot be easily implemented in an experimental scenario. So what we want in an experiment is that we should have something that can be expressed as a completely positive map. That's crucial. Now, another interesting entanglement, separability criterion is the collection of entanglement witnesses. Now, what is interesting with entanglement witnesses, say W, is that W is as a directly measurable observable. So notice that for all separable states and for some entangled state, they must satisfy these two properties. So we usually visualize witnesses in this way. So for example, the case in which we have the hyperplane, the trace of W raw is equal to 0. So we have this boundary here. So for all cases in which we have a positive linear functional here, we find that this includes the separable states. On the other side of the hyperplane, these states here can be detected by the witness. In fact, can be witnessed by the witness by using the language of it. Now, one crucial fact about entanglement witnesses is that we can always find a witness for every entangled state, and this is what we usually call the completeness of the witnesses. This has been proven using, I think, the Hahn-Banach theorem, and pretty interesting. Also, there are two interesting things about witnesses. Is that first is they can be constructed via the maps from earlier, the positive but not completely positive maps. However, there we arrive at the problem which the witnesses that we construct using this are hard to implement in an experimental scenario, but they have the efficiency of these maps. So one can detect more witnesses if they can be constructed from these maps. This connection between the maps and the witnesses can be shown using so-called Choi-Jomukovsky isomorphism. And yes, so it's a good way of constructing these witnesses. Now, the second thing about witnesses is that they can be optimized. So we can maximize the number of the set of detectable entangled states. For example, if we have this witness here defined by this hyperplane, so we can optimize it in such a way that we can detect, say, the states. So we maximize the set that we can detect from here to here. So it's a good way of visualizing it. It's a good way of visualizing how we optimize witnesses. So the last separability criteria that I would like to discuss is these entropic inequalities. So this is not related to what we discussed earlier, not really remotely, but this has been first seen by Schrödinger in the 1935, which is stated that the best possible knowledge of a whole does not include the best possible knowledge of its parts. It took about 30 years for this thing to be quantified mathematically in something called quantum information. So quantum information, we would ask two things about it. So the first one is how much is there to know and how much do we not know? So how much is there to know is something related to how much in quantum information can we get from the system. So it was formulated by Schumacher and I think in the 1995. So we defined quantum information as the um, number of qubits that we need in order to faithfully describe this information. So this can be shown using the von Neumann entropy given this. So notice that we have an entropy that is a nonlinear functional of the state. And the next question is, how much do we not know? So it's like, so suppose that we have, say, an Alice and a Bob system. And suppose that Bob wants to know how much information does he need given his information such that he can completely describe the state of Alice's. So this is related to a quantity known as the quantum conditional entropy, which is given by this. Now notice the similarity with the classical conditional entropy. Just in case, instead of the von Neumann entropy, we have the Shannon entropy. Now for the classical case, we know exactly that this is greater than or equal to 0, since you always need some information from Alice. So Bob still needs an information from Alice in order to describe her system. Now, for the quantum case, this can be negative, which is quite interesting, since it means that we know the entire state that well, but we don't know the state of individual subsystems quite well. So we have a negative conditional entropy. Now, if we have a negative partial, so if we have a negative quantum conditional entropy, this means that we have entanglement, since it is impossible for classical states for this to be negative. Now, this means that Bob doesn't need information from Alice in order to completely describe her state. What he needs, what he have is some free information that he can receive. So this was exploited in quantum information processes, since we have a free resource of transmitting information. Now, one way, there's also another formulation of the entropic inequality. It is in terms of the Renyi entropies. So the state is separable if both of these are satisfied. So I forgot to mention that raw A and raw B here are the reduced states of the entire state with respect to Alice's and Bob's. Now, this quantum Renyi entropies can be are defined in this form. And notice that if I choose alpha equals 2, so we can get an expression involving quantum purities. So if we have the separable state, then they must satisfy this. Now, this took about 20 years before it was experimentally verified and this experiment. So this can be verified experimentally by noting the anti-coalescence and the coalescence of the photons emitted by two sources. So we have two sources here of entangled pairs, and then we have a source here of two entangled pairs, and we have a source here of two entangled pairs. And what do I mean by anti-coalescence is that if they don't,
Joshua,
yes.
You are much longer than, so try to get to a conclusion.
Okay, I'm almost done. Sorry. Okay, so it's anti-coalescence is that both detectors detect it, and coalescence means that one detector detects them. So why do we do these? Why do we want a good detection scheme for entanglement? Because of its applications. So um, one famous application is a quantum teleportation, in which one can send the information of the photon from Alice's to Bob's, and this can be done by expressing the total initial state into this. Alice's measures in the bell in in some basis, and then tells Bob um, using two classical bits what he needs to do in order to get the information of the photon. So we have so I'll give you these takeaways. So entanglement is strange. There's no question about it. It's too strange. And that applications of entanglement, say quantum teleportation, quantum cryptography, and so on, needs detection schemes that are reliable and efficient. And as of the moment, there are no detection scheme that can fully distinguish separable states from entangled states. So that's all. So thank you. So,
Thank you.
Okay, thank
yes.
you.
Oh, other questions or comments?
So I had a question
Yes.
concerning the quantum key distribution thing that you
Yes,
showed
yes.
to us at some point.
Yes. I missed it. This one, yeah.
Yes. So my question is basically the idea is that here we can see that the things that we transmit to the observers have been measured on, and so they've been tampered with.
Sorry,
Because
I missed it. Sorry.
so we basically can see that the data sent to the people that do the measurements have been tampered with and corrupted because we violate the Bell inequalities.
Yes.
But this violation is something that you see with just one measurement, or you need to do many of them and then it's a statistical thing?
Yes. It's a statistical thing. You need to do it plenty of times in order to see it. Yes.
Because there are mean values involved, I see, in the
Yes.
inequalities. Okay, thank you.
Okay. Hello, everyone. I have a question now.
Yes, please.
Okay. I go to slide 6.
6. Okay. This one?
Okay. 5.
5. This one?
Okay. Where we have two interacting particles. Yes. I just want to ask, what is the distance between the two?
Sorry.
What is the relative distance of position of Alice and Bob that we negate the interaction property?
You mean that I would like to check if I'm correct. So what distance is between Alice's and Bob's subsystems such that the interaction remains the same?
Exactly.
Okay. So actually, it doesn't matter. The usual thing that you can see in popular media about this is that Alice can be in Earth, and then Bob is in Andromeda Galaxy, and the two particles will remain to be interacting. Yes, so it doesn't matter how far it is. Yes. So it's a weird thing about quantum entanglement is regardless on how far the experiments are where the experiments have been done, um, it is as if that the interaction remains non-local. So in the sense that if Alice's measurement on Earth as if signals bob on Andromeda Galaxy, and then the interaction still remains. But I want to point out something interesting is that the interaction here is not limited by distance. It's limited by its center. It's limited by the interaction of the two particles in the environment. So here the interaction begins to decay as the two particles continually interact with the environment. So in that case, the entanglement begins to disintegrate, and for some time, there will be no interactions, and that correlation will be zero. So that phenomenon is described by quantum decoherence, and I would not like to discuss any further about it. Yes.
So there is a question by Cossi. Do you want to?
Yes. Yes, please. Where is it? Sorry.
Can you speak yourself, or otherwise? Okay, I will read it since it doesn't seem he can talk. Cossi, can you talk, or can you unmute yourself? No. Okay, so the question is, can you explain a bit more about the EPR paradox? And you talk about in the first slide.
This one.
Yeah, yes.
That's quite weird. But it's actually I was planning on skipping it, but
So it will take a lot of time, I guess.
yes, but
Maybe
I
you
would
can
just like to add
later.
something about EPR paradox is mostly pointed out on the measurement weirdness that we discussed earlier. Is that it's as if the measurement on Alice's influences the measurement on Bob's, and that's a paradox. That's a sort of paradox, but what Einstein really pointed out in 1935 is much more of being simultaneously certain uh, of two quantities that are supposedly
Sorry,
non-commutable.
can you speak a bit more louder? I cannot hear.
Yes. Sorry. What Einstein really pointed out in 1935 is being simultaneously certain of two physical quantities which are supposedly representing two non-commuting operators. And this has been pointed out since it is a violation of the Heisenberg uncertainty principle. So yes, so that's where the paradox came from. But yes, actually that's where it came from.
Thank you. So when you talk this detection tools
Yes.
are theoretical tools. So you build these transposition maps and so on and so forth. So you can, given a state, you can test it whether it's entangled or not up to a certain extent, right?
Yes.
Does it translate into a possible measurement or not, or this is a different problem?
Yes. It's quite a different problem. Mathematically, one can construct these things here. The problem is they cannot represent any physical process in an experiment. So
yeah, you were referring to this, but the next one, the following ones, no, the same applies, or this is true for all the tools you presented.
For this one, for witnesses, it is possible. It is possible for the witnesses to be implemented in a physical, in an experimental setting. So for example, if we have some witness and we can only measure in terms of, say, the Pauli matrices, or say one can measure in some basis. For example, you can measure in 0, 1, so on. One can decompose the witness in terms of these, and we have just a an expression in which one can just sum all the all the all the contributions of those bases. So one can do that because this thing is directly measurable. So it's as if we can translate it into an expectation value. So this
Okay, thank you.
things here.
That's enough. Yes.
Yes.
So, are there
Okay.
other pressing
Yeah,
questions?
I have a question. So you
Yes,
have
please.
said that when you keep the when the two detectors are in 45-degree angles, then
This one.
Bell's inequality gets violated. Can you please
Yes.
tell about it a bit more? That why for these certain angles it gets violated?
Oh no, it requires a bit of calculation. Yeah. I can wait. Let me see if I have the solution here. Right. Yes. I think I can try to do it. Suppose that, say, Alice measures in the z direction, right?
Mm.
And then say Bob measures on the 45 degrees from it. So suppose that this measurement is so we can express n dot sigma as 1 over square root of 2 the sigma x plus sigma z. So we can do that. And then what we find in this expression here. So sorry, we can use this instead. What can I find here?
It's
Sorry.
okay if it is too complicated. I just wanted to know that if any simple or quick answer you have, but it's okay.
Yes, yes. Yeah.
Okay.
If you one can Alice can choose a, say, z, and Bob
Mhm.
can choose sx plus sigma x plus sigma z over square root of 2, for example. And then Bob can also choose the same measurements. So Bob can measure in the sigma z and in the sigma x plus sigma z over square root of 2. So if we try to find the expectation values of all possible combinations, you will find that this expression here becomes 2 square root of 2, which violates this inequality here since it's larger than 2. So that's actually the maximal value in which we violate the Bell inequality. Yes.
Okay.
Is it okay?
Okay, fine. Yeah, yeah, it's fine. Good. Yeah, yeah. Okay, thank you.
Thank you. So I think we really have to stop. I don't know if you have other lectures afterwards, but it's really 5 to 4 now.
Oh no. Oops.
Um,
Oh no, I'm sorry. Sorry.
Well, I think I mean the talk was very good. Maybe I mean exactly on the detection criteria you were very short, and maybe there was too much material all in all, and that result also they were much too long. So so probably you should have decided to cut something.
Yes, yes, yes.
And so but apart from that, I think it was very good. And yes, so
Yeah, the talk was good and detailed. It's explained quite nicely. And only thing it was too much of material, so that's why it took more
Okay.
time. So just to be precise on time from next time.
Okay, okay.
so take into account that in the future, I mean, and in the real situation, people cut you short. So under circumstances, you would not have got to talk about detection criteria at all in this context, no? So
I see.
because it was all overtime. So Okay. Thank you. So
I'm sorry, I would like something. I would like to add something. If you can please help me understand this. So we have I didn't add this in the presentation because I can't explain this, but it measures entropy in terms using many body systems. So if you can help me understand this, then
asking
it's
for help.
yeah. So if one
No,
can help me with this,
send us an email and we will direct you to the right people.
Yeah.
I am not the right person to explain it.
okay. So yeah, it's just
So kindness also not so